Okay, let's look at the next section. Actually, do we have time?
So for what we just did, so can the parabola cross over?
Yes,
So,
as long as the limit points are the same. Ooh, but it has to be less than that function.
no, I understand that. I just meant since, X is whatever we choose it to be, if your parabola crosses over, encompasses part of the diagram.
Ideally, it's not supposed to, but I just, for that example, I should have made a more narrow angle, like 1/4x. But yeah, nobody can. You want the graphs to be specifically above and below, because each value of x in that domain has to be true. Chapter 2, Section 3. What is that title? The precise definition of a limit. So what does it mean to have a limit to begin with? We know that the limit function looks like this. And there are a whole bunch of things around there. What is C? Well, C has to be an element that's inside some closed interval that defines our function. And f of C is actually the limit value. So as x approaches C, this was what telling us. As x approaches whatever value C is, then f of x, the function, approaches some value L, which is the limit value. This says C is an element contained in the closed or open interval AB. So in other words, f of x has to be a continuous function defined on the open interval AB. And C, in other words, as I said earlier, f of x is a continuous function on the open interval AB, which contains C for all the x's inside A and B, but possibly not at C. In other words, it may not exist at C, but we're going to see what the limit approaches. So as x approaches that value C, which means do we have to get to C? No, we have to get infinitely close to it. When we get infinitely close to it, will the function itself lead us to some value L? Let's look at the pictures, what this means. Here we have some open interval AB. And this is our function f of x. There's some value C inside that interval AB. It could be an open, it could be a closed, it could be a hole there. But at f of C, if it exists, it equals value L. So far, that's what we just talked about. What this thing says now, as our values, as we pick values on both sides of C, these values correspond, let's call this x1 and call this one x2. So in this case, since f of x is an increasing function and x1 is less than c, which is less than x2, then f of x1 is going to be lower than our limit. Now, as this distances between these close, as they get closer, closer, closer to c, what happens to the distance between the f of x and the l's? As my x values get closer to c, what happens to these the function values and L? What happens to those? They get closer and closer. So the closer that these get, the closer our y values become to L on both sides. So there's our L value. There's our C value. The closer we get to these, the closer x becomes to c, means the closer our functions get to L.
Is it wrong to, since you have x1 and x2, if you just took them 2 and 4, add them together, divided by?
No. Because, well, typically there are two ways. The distances, as you said there, these could be the same distance. They could be symmetric. There's, if this was 2 spaces, then that's 2 spaces. But it doesn't always have to be. If this side was 2 spaces and this side was 4 spaces, then I would use the smaller side. So if they're not symmetric, then you use the shorter distance because it's more accurate. Because this long one, who knows where it's going to go. Very good question. So as x gets closer to c, our functions get closer to L. That's what the whole purpose of the limit thing is. And this is where the hard part, not the hard part, the boring part of this course is going to happen in this next couple of sections. Let's look at example 1 in this. Let's work it out. Let's see what this looks like mathematically. Example 1 says this. Consider the function f of x equals 2x minus 1 near x equals 4. So if we look at this, we look at the limit as x approaches 4 of 2x minus 1, what does that equal? Plug in x. 2 times 4 is 8, minus 1 is 7. Remember, this is our limit value that's on the y-axis. So what this says is this. However, how close to x does x have to be for the function differs 7 by less than 2 units? So what we're saying here is this. What does x have to be so that this function differs from 7, which is this value here, the limit, by less than 2 units.
So getting as close to 7 as possible within.
Yes, what does X have to be? So within 7. Right. Okay, so what is Y equal? Y equals 2X plus 1. Or 2X minus 1, I should say. Simplify this, we get 2X minus 8. I want it to be less than 2. So far, so good? Because we want to know, here's the function. I want to be within 2 units from 7. And our function is 2X minus 1 minus that value we're getting to. It has to be less than 2 units. We're solving for X. What do we have to do here to get rid of X? Or to solve for X? What do we have to get rid of? Absolute values. How do you get rid of the absolute values? Yeah, because when absolute value means that if I drop the absolute value off of X, let's say absolute value of X equals 4, that means X can equal plus or minus 4. So when I drop the absolute value, I get that connection. Because 2X minus 8 is less than positive 2, which means it's greater than negative 2. Add 8 to everybody. Eight minus 2 is 6. So I have 2X. 2 plus 10 is 6. 2 plus 8 is 10. Divide by 2. So I get 3. 5. So what this thing says is this. In my X value, it has to be between 3 and 5. It's less than 2 units. So that when our function, which is 2X minus 1, so it's up 2 over 1. We have a linear function looks like this. So if I plug in 3 inside our function, we get 6, we get 5. And I've put 5 in there, 10 makes it 9.
So when it's saying less than 2 units, is that 2 units either side or 2 units?
Either side.
So 7 minus
The
2
distance in this case has to be less than 2 units. What does X have to be less than 2 units?
If it said, let's just keep it nice even numbers. If it's at 4 units, then it would be
2 on each side.
1 and 7.
Yeah. Because remember, we're looking at X equals 4. This is 4. So it's 1 here and 1 here. So it's within 2 units. And notice that this is 4 units, which is what we discovered. What we can look at here is from this value here, we can look at X minus 4. If we subtract 4, which is that, then we'll get negative 1 to 1. 1 unit to the left, 1 unit to the right. But because we're looking from X as being 4.
Oh, okay.
This is our domain. Our range is going to be from 3 to 5, which is 1 to the left, 1 to the right. Let's finally define limits.
So for the last example, with the answer we give, the answer would be 3 is less than x is less than 5.
Yes. But actually, the question was asking for us, how close to x equals 4 does x have to be so that that function differs from 7 by less than 2 units? It has to be either 3 or 5, so it has to be within 1 unit, positive 1, negative 1, or 3 and 5, yeah. I was off track there for a second. Okay, definition of limit. Let a function f of x be a function that's defined on some open interval a, b, with c being an element inside that interval. Then the limit of the function f of x as x approaches some value c is the number L, which is how we defined it. The limit of our function as x approaches c is equal to L. Now, how do we prove this? The limit of some function as x approaches c is L. So the limit of a function as x approaches c is L. What does all this stuff mean? We're going to introduce, instead of saying like x1 is less than c is less than x2, y1. No, now we have to introduce the formal definitions of this. Epsilon and delta are any small numbers. Close to 0. Epsilon and delta. We're going to refer back to this equation using epsilon and delta. Epsilon greater than 0. They have to be positive. So because they're positive, the function f of x and L, the difference between those two have to be less than some epsilon. So the differences from my L answer and the function where I am has to be less than some else epsilon. When our x values, x minus c, is less than some delta. This is how we have to, what we have to do, here's the ultimate goal. We have to algebraically manipulate so that these two absolute values are the same. And then we compare the epsilon delta. Remember, epsilon and delta are very small numbers. They could be like 0.0001. They could be a small. Now, what does this represent? This is delta, and this is epsilon. So the smaller these values become, that means the closer they get to C, that means the closer they get to L. So that's what we're gonna try to do. We're trying to get these values going to be very, 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 very small. So we can get infinitely close to X and the C value to X.
On the notes, are any small numbers close to zero? Is it zero or is it meant to be C? As I'm getting closer to,
It goes to C. Yeah, because the distance will be zero.
oh, okay.
Okay, so an example here, and we'll call it a day. Or call it a week. The limit as X approaches 1 of 5X minus 3 is equal to 2. Remember, we have this, it's shaped like this. What is the question asking for? Show that this is true. So remember, we here we looked at f of x minus L is less than epsilon when x minus C is less than delta. This is the procedure we have to use. So on this side, we have 5x minus 3 minus our limit 2 is less than epsilon.
Do we know what our epsilon is? Or is that what
This is given. Oh, no. Epsilon, sometimes it may be given to you. If it's given to you, then we can use it to find delta. But if it's not, then we just compare epsilon deltas. I thought you were going to say L. No. And the second part, the x minus C, this is x minus 1, is less than delta. Remember, the objective is we first have to solve this one. And then we compare the two. So we have 5x minus 5 is less than epsilon. 0 x minus 1 is less than delta. Now, we have to try to make these two the same. What can I factor out of this one? I can take out a 5, which leaves me x minus 1. Now, are these the same? No, because that still had a 5 coefficient. How do I get rid of the 5? Divide both sides by 5. So since those are equal, now we compare these two. That means delta is equal to epsilon over 5. And that's our proof. So for whatever delta you give me, it'll be whatever. So if you give me a delta, let's say it's 0.001 equals delta, I can calculate the epsilon, how close the y values are. So if this is 0.001 is equal to epsilon over 5, then epsilon multiply both sides by 5 is 0.0. So that's how close my function is to the limit.
So you get infinite.
Yeah. Basically, you'll never get to 0. Because if you see this, delta has to be always strictly greater than 0. And epsilon is greater than what of this, and this value can never be 0 because it's the function. The only way it can be 0 is if we have a constant function where the function equals a limit. And then in that case, any value x works. We'll call it a day there. We'll call it a week there because the next, we used to have a whole bunch of examples and they'll become more complex. All right, everybody, have a great weekend and use tomorrow to do the homeworks for the first 2 sections.